Hello Legacy Savers, Marsh here. So today we're going to talk about the real number system. Your learning objective, which you should write at the top of your notebook right under the title of this video. I can classify and identify numbers within the real number system. So here is a graphic organizer of the real number system. You should have it from me. We're actually not going to use it right now, but we're going to use it later in the video. First of all, though, we're going to talk about is the rational numbers and the irrational numbers and why they are split. So, rational versus irrational. Remember, guys, if you see this pencil in the corner here, that means write this down. Important information on this slide. So, rational numbers and irrational numbers. If you've ever heard of someone saying they have rational, they are being very rational today, that means that they are making sense, or their decisions that they're making are smart decisions. Irrational does not make sense. So if someone is irrational or having irrational thoughts, that means that they are not making sense in that regard. So, rational numbers, what are they actually? Any number that can be written as a fraction. So as long as I can change that number into a fraction, I can consider it a rational number, So, what do they look like? Fractions, 2/3. That's a rational number. Wholes, 7 or 7/1, because I can write that as a fraction, right? Integers, -18, because all I need to do is just put over 1 and I got a fraction. There's also a couple that are decimal-like. Terminating decimals, the terminator. They terminate, they stop. They do not continue to go on. Another one is the repeating, the ones that they have a pattern to them. You know what's going to happen. So like 0.7 would be a repeating decimal because it continues forever, naturally the same way. Irrational numbers now. Those are non-repeating and non-terminating decimals. So they cannot stop and they cannot repeat. So examples. Also, they can't be written as a fraction. One example, square root of 3. Anything usually with a square root, like the square root of 2, square root of 5, those are all irrational numbers. They cannot be written as a fraction, and they are non-terminating, non-repeating decimals. They just never stop. Also, I have a couple of other random decimals here that are not terminating. They never do stop, hence the ... dots after, and they never repeat. There's no pattern to them at all. So now, since we've talked about rational numbers and irrationals, let's delve further into the rational numbers side of our diagram. So if you notice, guys, that how the rational numbers, and then we have the little boxes inside, I like to consider them like the Russian nesting dolls. There is an item in the smallest box. It's also part of the larger boxes that it's inside of. So if you ever played with Russian nesting dolls or have seen them, basically what they are is a large doll, and if you open it, there's another smaller doll inside. And if you continue to open up these, you'll get to the smallest doll that cannot be opened. So we consider these as the rational number system over on that side. So consider the natural numbers the smallest doll. It holds the smallest amount of numbers inside. Whole numbers is just a little larger, just hold a little bit more. Integers, rationals, and real numbers. What does this mean to you? What this means is that natural numbers are also part of each doll that it can fit inside. So what that means is that if it's a natural number, it will also be a whole number, an integer, a rational number, and a real number. These are not exclusive categories. However, if I have a larger doll, such as the integers, it will not fit into the whole number doll because the integers do not fit in the whole numbers. There's more in there than the whole numbers. So consider in the box diagram, you can work outwards when naming, but you cannot work inwards. Okay? So consider that you can always work outwards as you're going. So, what does each of these actually hold? So the natural numbers, guys, are the numbers you naturally learn to count with. When you were a child, you started counting with 1, 2, 3, 4. They also occur in nature. Now, whole numbers, the only thing between naturals and wholes is all of a sudden we gain 0. So whole numbers is the natural numbers and 0. So the only difference is 0, really, because children do not start to count as, or start to count with a 0 when they learn to count. Integers as well, guys. Integers, the only difference here is we are going to gain the negative numbers. That's the only difference. So we're now going to have the -3, -2, -1, stuff like that. Okay? Something to keep in mind as we continue to work. So now, let's place some numbers inside so we kind of have an idea of where the first part of, where they would be the first part of their number system. So I got square root of 2. So square root of 2, that's like 1.7 something, and it keeps going forever, doesn't repeat, and doesn't terminate. So that is a irrational number. It does not stop, doesn't terminate, any of that nature. -6. So remember, guys, if you remember what we just talked about, -6 negatives started in the integers. So it's got to be an integer. Now remember, guys, since it is an integer, it is also a rational number as well, because the smaller boxes fit inside the larger boxes. 2.73, that is a rational number because it is terminating. Alright? Square root of 9. You're probably saying, well, it's irrational, Marsh. It has a square root. Think, I beg you to think a little better. Square root of 9, that is a natural number because all it is 3. Square root of 9 is 3. So please, guys, if you look at these numbers, please double check to make sure you simplify if possible. Because if you simplify, you may find yourself putting them into a different category. As well, do not associate a square root with irrational numbers. That would not be a good idea due to the fact some of them are not once simplified. Now I have 3/7. Remember, guys, fractions are rational numbers. I have -100. The negatives go with integers. 0. Remember, 0 is not a natural number because we don't naturally start counting with 0. It is a whole number. Pi. You guys remember pi from geometry. It's like 3.14159, something like that. Pi is a irrational number because it never stops, never repeats. It's one of the most famous irrational numbers, actually. 1 is a natural number. You start to count with 1 as a child. -1/2. Now, guys, just because it has a negative does not mean it's an integer. It is a fraction. So it has to be a rational number because it is a fraction. So your rational numbers can also include the negative versions of those as well. -3.8, it is a terminating decimal. Thus, it will be a rational number. I have 5.42. Now, that one is not terminating. However, it does have a pattern. It's going to be continually 42, 42, 42. So it is a repeating decimal. Thus, I'm going to put it into the rational number category. I have 8.293017 ... So that one is not repeating. It is not terminating. Thus, it is an irrational number. Then I have -18. That is an integer because it is a negative and is not a fraction, though I could write it as it. And 75/15. That is not a rational number. You're probably saying, well, it's a fraction, but it's not because, guys, I can change that number into 5. 75 divided by 15 simplifies down to 5. So be very careful. I implore you to make sure before you start any of these problems, double check to make sure you do simplify your numbers. Now, let's look at these. Let's look at identifying numbers based on if it's a natural, a whole, an integer, irrational, or irrational. So, I have -4/5. That, it's not a natural number. You don't count with -4/5. Whole, remember that was just the natural numbers with 0. It's not an integer because it's a fraction. So it's got to be at least a rational number. And since this entire thing is the real number system, it is also a real number. All of these, as of right now, will be real numbers because they exist. -9, now it's not a natural number. You don't count with -9. It's not a whole number, but it is an integer. Now, since it's an integer, guys, we can work our way out of our diagram. So then, if it's an integer, if I go further out, I'll hit the rational numbers. Now, guys, remember, if you are on the left-hand side, you cannot go over to the irrationals. The irrationals are their own piece of the real number system. However, he is still a real number. Square root of 16. I bet I didn't catch you this time. Square root of 16 is just good old 4. So, I do count with 4, so he is a natural number. Now, since I have the smallest box, I get to go outwards towards the larger boxes. So, natural, it is a whole, it is an integer, it's a rational, and finally, it is a real. So, guys, do not assume that these categories are just exclusive. Some of these categories, some of the numbers you're placing will be in multiple categories due to the fact of where they are. Negative square root of 25. 25, square root of 25, that's all that is just 5. So all I have is -5 there. Not a natural, not a whole. It's got to be an integer because it has a negative in it. And it's not a fraction as it stands. I can write it as a fraction, however, so it's got to be a rational number. And then it's a real number as well because it's a real number system. Square root of 8, guys. If you do that on your calculator really quick, it's like 2 point something something something. Doesn't stop. Doesn't repeat. So it is an irrational number. Now, be aware, please. If you are irrational number, you cannot be natural, whole, integer, or rational because natural, whole, integer are included inside the rational. You cannot jump over to the different sides of the rational, irrational sides. But if it is irrational, you can also still be a real number. Something to be aware of. And that's the end of this video. See you later, Sabers.